Swayam Prabha. Educated India.
Next one is, now the next 3 sessions is we will look at design issues. Now we have seen so far what are analysis based issues. In other words, you are given a certain, in all these cases I had given a certain section and I had given pressures and you are checking to see if they are effective. Let us start with again you can have impulse based design for impulse loading or impulse response I should say, or you can have for dynamic or quasi static. Now let us start with there are 2 different, and I will present a couple of different methodologies. So we will discuss 2 approaches. The first one is we will look for an impulse based design the response. If you look at the resistance curve, the response or the resistance curve is also going to be your response. You know, that is another idea that again coming from a static world or where your design, you think the response is based on structural analysis, right. You are applying a loading and structural analysis gives you the response. But now looking at it from a different perspective, this is the limiting, the resistance curve for example, this is your limiting case anyway. So your response, you already know the response in other words. If you calculate this value and you know you are assuming rigid plastic, you kind of know the response already. So the resistance curve, and let us say this is Rm and this is Xe and Xm. For especially for concrete structures where theta is less than or equal to 4 degrees, and we have seen 10 degrees as the limit for low limit of protection. So sort of medium, this is medium level of protection, you can still get this response. On the side, the work done, if I look at the area under the curve, so this is Rm multiplied by Xe by 2 plus Rm multiplied by Xm minus Xe. So this is the work done, and using the impulse momentum principle, we have seen this before, plus kinetic energy equal to the potential energy, these 2 principles, you can derive the work, the energy into the system in terms of impulse as I square area, this is area square divided by 2 KLM multiplied by m. So this would be the basis for an impulse, again this is for an impulse based response, you need to go back and check for it. So let us, and there are some simplifications made in this example. So because we have covered, so what approach we have taken is you have covered all the basic principles, but if for the problem itself there are some simplifications I will talk about. So the example here is to design an RC wall, basically the depth of the wall, and the area of reinforcement. We will not go into detailing. Two things. You can use this for design of steel sections as well, just using similar principles as I had talked about, for the following loading. I had the problem in the SI system of units, and thank you to Rauf for converting this into FPS. So, the data that is provided, there are actually some very interesting ideas. I mean, in design, people have gotten quite creative to come up with procedures for design purposes. We will talk about all of that in the next couple of days. So, it is given that TD is equal to 4.83 milliseconds and IR is 730 psi milliseconds. So, we assume impulsive response and check at the end, check the assumption at the end. Hopefully, they match up. So, first step here is for the cantilever, it is just the reverse of it, but we will apply the principle shown above. So, for the cantilever, find the Mn. So, let us say you have a cantilever here and that is your PR. The cantilever height is given to be 10 feet and this is the height H, and your reinforcement would be in the tension side. So, this is, let us say, AS. So, you are required two things, we will find as AS and H given, and of course, we are assuming 1 feet width. So, this is B equal to 1 foot. So, for a cantilever, to find Mn and Rm, we know that we start with, we just go through the reverse process. So, Rm is equal to, and you can see as it is where we are going, M Rm, let us say, divided by L. Now, you can write M Rm is equal to rho Fy d square. So, rho B d square, basically if you see, this is in terms of rho Fy times B d square concept, where B is equal to 1 feet. If it is something else, you can express it. The effective depth H is this is effective depth is D. D there. So, here combining these two, I can write Rm is equal to 2 by L rho, this is again of steel, multiplied by Fy dynamic multiplied by d square, and Fy dynamic is 1.2 into, and do not worry too much about the numbers. Let's go with whatever we have calculation wise, but you can change those numbers as we have seen and as appropriate. This is for the reinforcement. We have done structural steel, this is for reinforcement. And so from here, idea is to calculate an expression for, or get an expression for Rm as L is 10 feet. So this is 10 times 12 inches. So you have, and rho itself is this is the percentage of steel. So let's assume this to be 0.5%. You need, there are two variables, rho and d. It's hard to work with both at the same time. So we can assume rho and find d, or you can set up an Excel sheet or whatever you use for for changing. You can use this procedure for changing rho and h and finding h. So you can use an iterative procedure. So here we are starting with assuming rho of 0.005. So Rm comes to 2 by 10 times 12 multiplied by 0.5% multiplied by 87, this is in PSI, so this is 1000 d square, or Rm can be expressed as 7.5 d square. D is in inches. Again, this is something for you to note. Anytime you have numbers like this, you reduce it, always add this, what units are you expecting D to be in, because these numbers, they don't tell you any story, and the whole thing is in pounds. Then second step is assume the LOP. Now in this case theta is equal to 4 degrees given. So the and find x max. So you want a medium level of protection. So this is xm L by 2 and this is 4 degrees. So xm is equal to L by 2 multiplied by, I am sorry, this is a cantilever. So cantilever so this is xm and you have here L and that is your theta. So xm is, you will not have the 2 here, L tangent of theta. So L is 10 feet. So you get xm maximum equal to 8.28 inches. Then next step here is to find the K of the cantilever, stiffness of cantilever. And the stiffness now we do not know because the H is not known. We, for a cantilever section, as we know, simply supported, I am sorry, cantilever section, continuous loading, this is 8 EI by L cubed. So K is equal to of course multiplied by your WL, I am sorry, this is WL cubed by 8 EI, WL power 4 by 8 EI. So, K is equal to 8 EI divided by L cubed. So, EC, this is 4.9. Again, these numbers at this point, typically these are a little bit lower. 4.9 is perhaps a high strength concrete. Normal strength concrete is about 3.6 into 10 power 6 psi. I can be taken to be I cracked, but we do not know reinforcement. So, reinforcement is unknown. I am sorry, reinforcement known, but the depth unknown. So, here we used Ig, but let me make a note, better to use IE, which is Ig plus average. So, let us go with this. So, Ig is BD cubed by 12, which is basically a simplified form. This is D cubed, this is also 12 and 12. So, basically 12 D cubed in inches per 4, making our calculations a little cleaner and simpler, but you can see the effect of it can change. So, K now comes to here 8 times 4.9 into 10 power 6 D cubed divided by L. So, K comes to 226 or no 22.68. Let us say 22.7 D cubed. I think it is in a different page. The page differentiation is a little not very clear here. I do not know if you can see it, but I can't seem to. Yeah, there is a light one, but anyway. So, K comes to 22.68 D cubed. Again, D is in inches. So, we are getting everything in terms of one variable now. So, then the next step is to find XE, which is we have seen XE is equal to RM by KE. Lot of it is the reverse. This is 7.25 D square by 22.68 D cubed. So, this comes to 0.32 by D, and D is in inches. Then fifth step is your moment expression or the mass, sorry. So, the mass of concrete, this is the density of concrete multiplied by L multiplied by D, and this has been computed to 0.00023 multiplied by L multiplied by 12 D. So, this also comes in terms of 0.33 D, and KLM is 0.66. So, the number 0.33 includes 0.66, Rav? No, okay. So, we use these two expressions. Now, we have this, then use the energy principle equation or where you have I square A square divided by 2 KLM M equals Rm Xe by 2 plus Rm. So, you can see it is a fairly straightforward procedure for certain scenarios. We have assumed rigid plastic in this case. So, this comes to I think I had given I as 780 or was it 730. So, this is 730. So, either say 730 psi milliseconds. So, I is 730 psi milliseconds, but you need to take in terms of seconds. And use that here. So, this is 0.73 and the area is height multiplied by width square and 2 times 0.66 multiplied by 0.33 d equals to 7.25. The Rm is 7.25 d square multiplied by Xe. Which one? Yeah, this is Rm Xe. This can be simplified further. Here it is Rm Xm Xm minus Xe by 2. So, that is what we are doing out here. Rm, this is Xm minus Xe by 2. So, this one comes to 8.28 inches minus 0.32 by 2d, right? Yeah, 0.32 by d, Xe by 2. So, 2 multiplied, so Xe by 2d, no, Xm. This is Xe by 2, but Xe itself is a function of, so this is Xe by 2. So, this is 0.32 by 2d. So, from here you can calculate, solve for d, and d comes to 34 inches. So, h is 34 plus another 2.5 inches, 36.5, or let us say this is fairly large. You might even question, is it a question is now, as I look at it, is it a true cantilever? Because your L by D is roughly around 40 inches by 120 inches. Close, I guess one third should be fine. Typically 3D, 5D is better. And your required reinforcement ratio is rho times A is rho times BD. So, 0.005 multiplied by P is 12 inches multiplied by D is 38 minus, let us say, the 2.5 inches comes because you are providing here the steel. This is H, and typically this comes to around 2.5. So you can calculate this in square inches. But it is high because impulse is high. So, this is one straightforward way. Let us just check, and I think I do not have the calculations with me here. Let us check our assumption. So, please help me with it, of impulsive response. So, we need to calculate Tn, which is 2 pi square root of m over Ke. So, Me is 0.66 multiplied by, we have provided a little bit more. So, D is how much? 2.5 and we said 38. So, this is 35.5. So, rho is 0.3, mass is 0.33 D multiplied by D is 35.5. So, how much do we get here? About 7 or 8? 7 point? Always try to have an idea of where you should land somewhere. So, then your, no, this is mass, sorry, then Ke was 20, what was it that we calculated? 22.68 D cubed. And this would be, I think, in pounds per inch. Should be a large number, right? 1 into 10 power 6? Okay. So, hopefully, this is a reasonable number that we get. I don't. This is pounds or kips out here. When we did this 0.0026, the mass was, do you know what it was, the mass here? Pounds, right? Okay. So, what do we get for T? Seems to be fairly large or fairly small. And so, this is 7.73 0.017. Okay, that makes sense. So, 17 milliseconds, and I haven't given TD, I haven't given it PR, I have only given an impulse based. So, P is given, T is how much? Oh, 4.83, okay. So, TD by Tn is 4.83 by 17, 0.3 something or 2.28. So, which sort of falls, so there is another typically there are 3 Td by Tn less than 0.1, then 0.1 is less than Td by Tn is less than 1, and then Td by Tn is greater than 1. This was quasi static and this is impulsive. So, we do fall somewhere here. So, our response may not be not ideal, but reasonable design. So, this is one way of doing things. It's fairly a straightforward method. Have any questions? Now, there is an alternate manner. Again, those are all, as we keep talking about here, there is no one answer. One thing you would have noticed as a common theme to all of this is it's not a definitive answer to most scenarios. So, the design approach, and alternate. This is a very nice idea actually. So, there are several types of systems as we have just discussed. Let me repeat it. One is a peak pressure sensitive system. What are the characteristics of a peak pressure sensitive system? Long duration. So, that also tells you to see if it is an impulsive type. If your pressure is high and TD is low, likely to be, and the response comes after. In nonlinear also, sometimes you have to be careful to give, especially if it is an impulsive type loading, in that the duration to which the applied is load. You are applying the load for 20 milliseconds, but then there is a place where you can say run it for 100 milliseconds. So, run it a lot longer to see where the peak is. And there also play around. We have initially talked about TD by Tn is low, medium and high, and then where the response, we have drawn a triangle. So, number of things you can try on your own. So, long duration, make sure you give that response time to be much longer than the loading duration, and it also gives you a relatively low. If the pressure value is low, the duration is long, that is one indication. The other extreme is an impulse sensitive, the example that we just did above, impulse sensitive system. So, this is characterized by short duration, where TD is less than Tn, and high pressure. And this approach we are talking about addresses all three systems. Dynamic system, that is the beauty of this approach. Dynamic system, it is in between, neither here kind of nor there. If just as some ideas on Tn ranges, if it is a heavy RC wall, the Tn is of the range of 40, 60 to and 60 milliseconds and above. So, this example was a heavy RC wall. Here it was, well, the length was not much. So, does not quite come under heavy because the mass, it lowers the mass. So, here we had 17 milliseconds. I think the last example, first example we did RC, that was 66 milliseconds. But these are just approximates. Light walls about 40 to 50 milliseconds, and on the other hand, on the other extreme, windows glazing systems about 1.5 to 2 milliseconds. So, goal is, in design we need the strength Rm. So, the example here, if you see, Rm was what was needed, that was in terms of d square. So, we need the strength, and then once you have the strength, you can use any design procedure that you know for that particular system. Then from Rm we design per the material used, whether it is concrete, steel, masonry, pre-stressed concrete, so on and so forth. So let's look at the two extremes. First is the peak pressure sensitive system. We use the energy principle or the energy balance. So let's consider here a graph of the force versus time, and you have, let's say, constant force over time. This is now, instead of time, we'll say this is the response y delta. So this is y max. So we assume that the force remains constant over the entire displacement. The response we have seen even in the previous example is so we'll use the same idea there. This is Rm versus y, ye and ym. So what we get here is the work done. So the work done is F naught multiplied by ym is the energy in the system, internal energy, which is Rm ym minus Rm, the same thing that we just derived. So let's manipulate this equation a little bit in the in a good sense, mathematical sense. We know the term mu. Mu is critical ductility ratio, right? So mu is the critical ductility ratio. What is it? Ym by ye. So I can write this expression as F naught ym equals Rm ym multiplied by 1 minus ye by ym multiplied by 2. So I get it in terms of what's a nice thing about this expression. Maybe I'll throw this question open. It's a very simple expression, right? Nothing fancy. But what is a huge advantage of expressing it in this way? From all the terms you have learned so far, think of what we need. What we need, Rm. What is the advantage of expressing? So let me put it this way. Let's just break this down. F naught ym is Rm. Ym and ym gets, wait, I forgot to take y. This is Rm ym, right? If I take ym out, Rm YE by YM. So, this gets cancelled. So, F naught is RM multiplied by, I would like to maybe just give it a, looking for an answer. So, my question is, what is the advantage of expressing the same term in this manner? Connected to something that we have done today. Some charts. I have shown some charts today. It's like tables, charts that I inserted as images. I am giving a lot of clues. Yeah, go ahead. LOP, right. So, mu represents, perfect, excellent, LOP. So, now I can get RM for different LOP, right. From this equation I can get RM, which is what I need for different LOPs directly. It's pretty straightforward, right. So, it's such a beautiful expression. So, we express this term as RMF is equal to RM, sorry. I will call this R, okay, M is fine, is nothing but the applied load divided by the term RMF, which is what we call this. I think it may be better to, so that we do not confuse it, let me, do not mind if I go ahead and change this to Rn, make this N, make this N. And so, let us make this N, because you have an Rm here. Now, this is what we call as the response modification factor. So, we have an applied load divided by a response modification factor, and we instantly get what Rn is. Once you have Rn, you can design a section, right. That is all we need. This is for an impulsive system. So, for an impulsive system, RMF is equal to 2 mu minus 1 divided by 2 mu. And yeah, so for concrete you are given, let us say, theta, great question, is equal to 10 degrees for low level of protection. Convert it into a mu. Here you have your delta m is equal to, this is L by 2, right. So, you can convert delta m is equal to L by 2 tan theta for that LOP, and then your mu is delta m by. So, find an equivalent mu. So, convert, so do that. If mu is already, if both are given, choose, in this case if you see, you have to choose the lower one. So, 1 minus, the lesser the value, greater here. So, you choose the lower of the two. Once you choose the lower of the two, this factor 1 minus 1 over 2 mu is the lower value. So, then you can, so if you are given, so this is one scenario. Second scenario is if you are given both theta and mu, find the mu equivalent and then choose the lesser of the two values. Now, just some side notes. If you have an elastic response, what is mu? Value. It's easy. 1, right? Ym, yeah, don't hesitate. So, this is Ye by Ye, which is 1, right? So, what does this tell you? For an elastic response, you have Rn is equal to F naught divided by 2 mu minus 1 by mu. So, basically Rm is equal to basically quasi static, right? You're not amplifying anything here. Wait, this is mu is 1, 2 minus 1 is 1, 1 by 1. So, Rm is equal to F naught, correct. What's that? Oh, sorry, you are right. So, 2 mu minus 1 divided by 2 mu, right. Okay. So, 2 mu minus 1, so this gives you F naught, this is Rn. So, F naught by 2. So, what you have is, wait, no, other way around, multiplied by 2. So, you get Rn is equal to, is this familiar? Remember we said for elastic response is 2 delta static, right? Elastic response delta dynamic is 2, same thing. You see, a lot of these stories are all hidden, can come to the same point multiple ways. So, just as an aside, you've all solved, so you have to think physically also. We just take a little side. You've all solved the, I mean you should have solved the basic sinusoidal, you have your expression dynamic natural frequency, right, to find your natural frequencies. Let us say a column, elastic column buckling problem, right. One of the solutions, it gives you the eigenvalues and we did that, you can calculate the natural frequency. The other solution is y equal to 0 is a solution, a is equal to 0, b is equal to 0 is a constant, both are zeros. Does that give you any information? Have you thought about it? Are you all clear on my question? Remember, just a natural vibration problem, simple, your second order non-homogeneous equation you are solving, and you get we did that. One was a vibration eigenvalue. The other solution is y equal to 0. What does that represent? Does it represent anything at all, first of all? What does y equal to 0 tell you? Well, what does y represent there? The lateral deflection, right? So in this problem you are applying a load, this is y. Y equal to 0 is a lateral deflection. Does that tell you anything? It does tell you something about something. I mean, it seems to be a meaningless solution, right? But what does it tell you? There could be no buckling, right? It tells you a situation where there is no buckling. So always look into, what is hidden. If 0 also conveys something to you. So here if you see Rn equal to 2F0 tells you the delta dynamic is 2. And look at the other extreme. If let us say mu is equal to infinity, it is going higher and higher. Then if mu is infinity, what do you get? Rn equal to F0. If you are designing for the applied force, what do you expect? A very high. And so what are your limits between the two of them? So you are designing for a low force, so you will get mu high. The other way to look at it is also let us start with Rn equal to F0 divided by 1 minus 1 over 2 mu. Let us start here. So I can write 1 minus 1 over 2 mu is F0 by Rn, or 1 plus sorry, not plus, minus 1 minus F0 by Rn is equal to 1 by 2 mu, or I can write it as mu is equal to F0 divided by 1, I am sorry, this is not F0, I can rearrange it. I get this to be 1 divided by 1 minus F0 by, let us just do it, I think I have got something wrong there. So invert it, so mu equal to 1 over 2 times. Okay, am I right? So now what do I get out here? Given F0, given Rn, if I know these properties, a quick estimate, we have done PI diagrams, but I can get a quick estimate of the level of protection, right. So you can use this in multiple ways. You can analyze a structure and find the level of protection with a quick calculation, or I can use this to design a structure given a level of protection. Same equation viewed couple of different ways. Let us look at the other extreme. Impulse sensitive systems. A lot of these ideas, again, it's not even used in structural dynamics. If you're designing for seismic design, none of these ideas are actually used the way we are looking at it here. Keep in mind, we talk a response modification factor. Be careful when you talk to people in a seismic design world or you're working there. It also represents ductility, but there it represents the ductility you're designing it for. There it's only one thing, you got a capacity, elastic capacity. Elastic capacity is whatever you're designing, and then you apply higher the mu, higher the ductility. It can go from 1 through 8. Costs vary for different systems, and so there it is used from more from what I have shown out here. The mu is equal to 1 minus F naught by Rn, but just keep that in mind. Now, assumptions in an impulse sensitive system is, we've seen that it is short duration. We assume that all energy, and that's not the case, as we were just discussing during the coffee break, that any concrete structure, it's going to, so Raghav is working on estimating, one of the projects he's working on with Professor Aragappan is to estimate the remaining strength of concrete structures due to, and then what effect it has. So here their energy is conserved, but it is dissipated in the form of the fragment, the spalling and breach. So applied system, impulse sensitive. So the first one was, what we did was peak pressure sensitive. So we started the other way around. Here it is impulse sensitive. So we start with F naught and Td. So I is 1/2 F naught Td, and then you also have the same Rm, the response R versus delta. All of these are again idealized. So keep in mind, these are derived for a rigid. So if you have something like concrete goes something like this. So you're sort of saying, you're idealizing it something like that, or you can make it more ductile. So here your impulse is integral f of t dt. K is Rn by Ye, and mu is Ym by Ye. So this is mv naught. So v naught is I divided by m. Then your kinetic energy is potential energy. So we have Im is 1/2 m v square is Rn, same thing, x or y m minus Ye by 2. So substituting 1/2 m, we have done this before, but we'll look at it from a slightly different perspective. You saw the first equation that I proposed, that I showed, we did one example. It's based off of the same principle. Rm Ym minus Ye by 2. So the left hand side comes to I square. If you see the expression, we had I square by 2 KLM multiplied by m, right, multiplied by A, of course, in the first problem. Same, it comes from here. So now here we'll do a couple of manipulations here. So we will say this is, let us say, ym by ye minus 1 over 2, just like what we did. Then I will take ye out, and I know that y. So if I take wait, if let me make sure what I am doing. So if no, I have to take ye out. So that's how I will get 1 over 2. So if I take ye out, I get Rm ye. So now Rm multiplied by ye is k. You have here Rm divided by k. So what's that? Multiplied by here, if you see, mu minus 1/2. So am I missing anything? So you have here Rn square, and what is omega? Square root of k by m. So what you have is k is equal to m omega square. So Rn square divided by m omega n square, 2 mu minus 1 divided by 2. And this is I square divided by, not 2i. So no magic here. If I am making any magical errors, point out. So I square divided by 2m. So I can cancel 2. See how nicely some things fall off. And what you get now is Rn is a function of I omega n divided by square root of 2 mu minus 1. So in design now, we need Rn. So we can say Rn is equal to I omega n by square root of 2 mu minus 1, which is 1/2 P naught Td multiplied by omega n by. So we have a very nice expression again given LOP mu P naught Td, find Rn and design. If you need to check the LOP, so before that we'll just go over a little bit and finish it off. Now I can express this Rn as slightly in a different way. I can say Rn is equal to, and knowing that omega is equal to 2 pi f, which is 2 pi f is 1 over t. So 2 pi by Tn. So using that also we can now express this as f naught divided by square root of 2 mu minus 1 divided by pi Td over Tn. Or F naught by RMF. Some creative individual, I don't know if I know who it, I mean, I tried looking for references, original, but I'm sure I haven't searched hard enough, that's for sure. So they came up with now the response modification factor here as square root of 2 mu minus 1 divided by pi Td over Tn. So you can design, and if you need for analysis purposes, you are given Rn, F naught, Td, Tn, you need to find mu and the LOP, then mu is given as 1/2, you just rewrite it, you get I square omega square by Rn square plus 1. Interestingly, R is equal to Rn is I omega, if for mu equal to 1. Mu equal to 1, we saw an elastic system. From here you get Rn. Sort of strange quantities are sitting together now, right? You would have never thought of I and omega together. Have you ever thought of I and omega to use it in any way? Have you ever done it anything like this? No, in design. I mean, we've never used impulse in the first place. If we use impulse and then combining with a natural property, it's, why is it instantly make sense? What does I represent? Huh? What's the physical representation of the impulse? Yeah, time and pressure, the load, right? So it sort of represents, now if you have forces, k times x, right, and you're designing for kx. Here it is I, instead of displacement it is angular circular velocity. So they are analogous to each other. So this is a strong for a elastic response, and we'll look at, I think it's past, we'll look at these and a few examples maybe tomorrow.